Problem one, we have a piston moves without friction in a cylinder of section S1 and diameter D1 filled with water. As you know, we have the cylindrical object. Inside we have a piston. We can push the piston. We can push the piston without any friction between the body of the piston and the internal wall of the cylinder. I give you, I give you the value of S1. No, we have D1, which is equal to 4 centimeter. And we have water. We can take the density of the water equals to 1000 kilogram divided by meter cube. Okay, I push the piston with F equals to 62.8 Newton to the right with a constant velocity. We have a constant velocity. I give you the diameter at the outlet. We have D2 equals to 1 centimeter. And you know at the outlet at this point is in contact with the external medium where we have P0 at this point, only at the outlet, which is in contact with the atmospheric pressure, P0. Okay, now I ask you to determine the pressure P1 in function of F, PO, and D1. I need to calculate P1 in function of F, PO, and D1. You know, here we have a dynamic configuration fluid. We have two functions or two equations to use. We have Bernoulli equation and we have the continuity equation. But here, you know, we have to calculate P in function of F. So we can calculate directly its value by applying Newton's second law. We have simply a piston. From the left side, we have F applied by an external agency. And we have, you know, for any object, we have the value of P0 applied on the object where we have FO. PO equals to FO equals to PO times S1. You know the section of the piston is the same as the section of the cylinder. We have the same area, the same cross-section area. So from the left side, we have F and we have FO. From the internal side, you know, we have gas, we have water. As we have water and we have a small outlet, in this case, if I push the piston, the water will have some resistance, okay? We have some pressure applied by the water on the piston. We can say here we have P, or we have F applied by the water, you know, which is equal to P of the water times S1. Okay? And you know here, we can apply Newton's law in function of x-axis. Just I take F in function of x, which is equal to FO plus F plus F water equals to MA, the mass of the piston, times A. You know we have a constant velocity, so equals to O, as V is constant. Okay, we do the projection in function of x prime x. We get here the positive direction to the right. We have F plus FO minus F water equals to O. As I want to calculate P1, P1 is P water, okay? We can say here P1 or P water. So F is given plus FO equals to PO times S1 minus F water equals to P1 times S1 equals to O. We can calculate now P1 in function of F times S1. I need to calculate in function of D1, not S1. We can put S1 in function of D1, where S1 equals to pi times D1 divided by 2 square equals to pi r square. Okay, divided by P1 S1 equals to pi D1 divided by 2 square. So here we have a function of P1 in function of F, PO, and D1. Okay, this is the value of P1. You know, if I use Bernoulli equation, we cannot have this function because we don't have the value of F inside Bernoulli equation. So we can use Newton's law to find P1 in function of F, PO, and D1. So this is the value of P1. Let's go to part 2. We can put it here. Part 2. I need to calculate V2 as a function of P1, PO, and ρ. We find V2 in function of P1, PO, and ρ. Okay, as we have P1, V2, all these parameters, we can apply Bernoulli equation and the continuity equation. You know, always you can use Bernoulli equation and continuity equation to reduce the unknown variables. Okay, here we have, by using Bernoulli equation, we have P1, we have P2, H1, H2, V1, and V2. If I put, by using the continuity equation, V1 in function of V2, we can reduce V1, okay? We can reduce the unknown V. Okay, here I need to calculate V2. We can choose 2 points, a point here, 1, and a point at the outlet. We have a point 2. We can write the continuity equation. You know, A1 V1 equals to A2 V2. And P1 plus rho GH1 plus rho divided by 2 V1 square is a constant value at any point inside the medium. We can take at the point P1 or at the point P2. Okay, let me calculate the values of each variable. Here we have P1 is calculated before, it's here. Anyway, I want to calculate V2 in function of V1. I don't need to put P1 by its value. We have H1 equals to H2. You know, here we have H1 and here we have H2. They have the same height. We can say H1 equals to H2. So rho GH1 equals to rho GH2. P2 equals to PO. So we can have finally rho divided by 2 V1 square. I put here V2. Let me write like this. Rho divided by 2 V2 square. This one. Minus rho divided by 2 V1 square equals to P1 minus P2. Okay. Okay. Look here. We have V1 and V2. I need only V2. We can use the continuity equation where V2 or V1 equals to A2 divided by A1 times V2. Okay, so we can write rho divided by 2 V2 square minus rho divided by 2 V1 square. Look here, V1 square equals to A2 divided by A1 square times V2 square equals to P1 minus P2. I need to calculate V2. So we can write V2 square here. I come back. I have a problem with my video. I come back to this function, to this point. You know, we can take a common factor V2, which is equal to P1 minus P2 divided by rho over 2, 1 minus A2 divided by A1 square. Okay, we can put A2 and A1. Look, A2 divided by A1 equals to pi D1 pi D2 over 2 square pi D1 over 2 square, which is equal to, we can eliminate pi and pi, 2 and 2. We get here D2 square divided by D1 square. So A2 square divided by A1 square equals to square. We get here 4 and 4. Okay, we can write directly P1 minus P2 divided by rho over 2, 1 minus D2 power 4 divided by D1 power 4. Okay, this is the answer.